All right, so let's get started. So a few heads up. First of all, next week will be our midterm. So the timing is the same. And it will be a closed book exam, and the coverage will from lecture 1 to lecture 3, which means we'll finish memory management today. And there are some advanced topics. I mean, there's a shown in the title in some slides that they will not be in your exam. So because we have like 300 something students there, so we will split folks into several rooms, like this room, ED102, and also some other rooms on the third floor. And the second one is we'll announce our second hands-on later today. Okay, so FSQA. Actually, there's a lot of QA, but I just integrate with the recall part, so we will talk about it later. And I think one of it is about IOMMU. I saw there are a lot of IOMMU questions here. So IOMMU can greatly reduce the need for zone DMA, and this is true. But the thing is, consider the goal of Linux. Actually, Linux maintains these memory zones to ensure board hardware support. So, I mean, for general devices, they support IOMMU now. But I mean, for some like edge devices, if they don't want to sacrifice too much of performance or they don't want to spend too much of power costs, probably they will not have IOMMU. And also, even all of those devices, they can support IOMMU. But in terms of Linux goal, actually, it needs to make sure the backward compatibility. So actually, zone DMA and zone no more, those kind of stuff, they're still in Linux. But I mean, if you choose a latest version of Linux, those kind of zones will not really affect too much. Okay, so quickly do some recalls. First of all, we are talking about memory management. So in Linux, there are virtual and physical. So we need to make sure like which data structure is maintained for virtual and which is maintained for virtual. So for physical address, you can think about it as about the location where data actually stored on the DRAM or on the device. So that kind of data structure people are using is called patch frame. Okay. And when we talk about the virtual address part, like usually is the location where the programmers think the data is, because the programmers, they do not really know where the data is stored on the DRAM, right? When you are writing your program, you don't know where the DRAM location is. So this is the reason why we call virtual. I mean, there is an address space, but it is not really really one-to-one map to the physical DRAM part. And for those kind of virtual address space, they are maintained by using patch. Okay, so last week we focused a lot on patch frame management. And this week we'll talk more about the patch. Okay, so as the system knows, they're using MMU. So even the CPU has the capability to do the bind addressable management, because come to think about when CPU is interacting with the CPU cache, actually this is aligned with the cache line. And the cache line is in the 64-byte size. So it is way smaller than the patch size. But because MMU inside CPU, it manages the memory part, MMU usually align with the 4 kilobyte size. So actually memory is in the patch size of 4 kilobyte. Okay. And no matter patch and patch frame, their size are all 4 kilobyte. And when we talk about patch frame, actually, like if you have a 4 gigabyte DRAM, then you can do 4 gigabyte divided by 4 kilobytes. So you get like a million of patch frames. So to manage those patch frames, we need a data structure. So in Linux, structured patch is the data structure or patch frame. Okay. So there are several flags here, just like if this is the dirty or if this is patch frame is locked or not, and how many reference, like how many process using this patch frame. Okay, and if this patch frame is related to the patch cache or not, and there is an offset if the patron, like it is swapped out to the disk, then there is a offset to point to the location on the disk. And also what kind of patch replacement it is using. And because this is a patron, so it is a physical, it does have a physical address, but actually it still have a counterpart, the virtual address part. So actually there is a virtual pointer. Okay, so we also talk about the overhead. Actually, it is not quite large because even it's a 4 GB DRAM, but the memory only consume like 40 megabyte. Okay, so even you use a larger, DRAM, for example, 16 or even 1 terabyte of DRAM, but the overhead scales linearly, so it doesn't really have that much of impact on it. And the next part we talk about is like how to manage kernel physical address. Okay, so actually there are 3 layers. The top layer, the top layer is it's about the uniform memory access or non-uniform memory access part. So because there are 2 different architecture, the left-hand side is the uniform memory access, we call it UMA, right-hand side is NUMA. So for UMA, actually, when CPU is going to access the data on the DRAM, it needs to talk to the memory controller outside the CPU. Okay, and this is the structure, I think it's before 2019. And after 2019, we say there is no North Bridge, right? Because North Bridge, the memory controller is now integrated with the CPU. So when memory controller is integrated into the CPU, and the thing is, when CPU is going to access the DRAM close to the CPU, then it is called a local access, which means you can have a faster response time. But the thing is, when the CPU is going to access the DRAM far from that is not attached with the CPU, then we call it remote access because you need to talk to other CPU to get the data. So for NUMA, there are several reasons. I think the most important is fast local access and higher bandwidth here. Okay, so this is called a node label. The reason we call it node label is because that's a pair of DRAM and CPU, it is called a node. So when the architecture is using the NUMA, we call there's a NUMA node. When the architecture is only using the UMA, the UMA, then we call it the UMA node. Okay. So when there are several CPUs and you have a lot of DRAM, and when your kernel is going to manage the physical address, like how to allocate a physical address, the process, the top tier priority is to judge whether the location of the data or whether your allocated part is near your CPU or not. Okay, so for this diagram, actually the top tier is the maintenance data structures, and the first data structure we'll consider is about the node part. So if it is kind of in the NUMA or it is a UMA, okay, and then after the judgment of the NUMA or UMA, then it comes to the zone. Like there are different zones that time we talk about. There are DMA, normal, and high memory. And actually, DMA is for the for some ancient devices that are they need to have a physical address pre-allocated for DMA. So there is a zone DMA area. Usually, this is a super small area in modern systems. And most of the data, they are in zone normal, okay? And zone high memory, this is for the dynamic mapping for the kernel address space, okay? So after this allocation, after this classification, at the bottom part, you will see the structure page, like the pattern part, okay? But what is the policy to do the allocation? I mean, for zone normal, for example, there are gigabyte, or even if you are using 64-bit systems, then you will have 256 gigabyte for the kernel. So actually there's a lot. Then how to do the allocation? So this is our physical DRAM. And then above, we have 2 different kind of allocator. One is for the user space, another is for the kernel space, okay? So no matter using which allocator, there is a thing called body system. So body system helps to partition the physical DRAM into I would say like a nearly fixed size area, but there are some smart policy to do the partition. Okay, so we will talk about it later. And this policy system actually aligns with the patch granularity. So the smallest granularity, the smallest size will be the 4 kilobyte, but you can get larger with the body systems. Okay, so for the kernel space memory allocator, there are several ways. The first is about for smaller size. Usually it is for data structure, because the reason we have this kind of standard of kernel memory allocation is because kernel is a static thing. I mean, those data structure for process, for memory, for file, actually they are all static, because you will do the compile and then you will run the kernel. So actually, when you are running a kernel, those kind of data structure will not change. As they will not change during the runtime. So this is the reason why kernel has more different kind of strategy to do the management part. So Slather is a thing for Linux kernel to manage their data structures. Okay. But there's also some other than data structure, like some dynamic memory when kernel is running, and maybe there is some dynamic memory usage. So for kernel, they will use a virtual memory allocation, vmalloc. So this is the reason for big size and small size. Okay. So the left-hand side, actually, user space memory allocation. The most famous one is the C library when you're using the memory allocation stuff. Okay, and then there are also two ways. One is BRK, another is like MF. So MF is for super large size, and then BRK is like usually for growing like hip, this kind of stuff. Okay, so allocate page, or usually people are calling body system. So body system is more like this. Actually, for body system, it will maintain this kind of structures from order 0 to order for maximum order. So this is the exponential part. So you can think about like for the maximum order, the system will maintain 2 to the maximum order size of the contiguous physical pages. So for example, 0 here means 2 to the 0 is 1. So there is size here is kind of 4 kilobyte pages. So for like this, 2 is 2 to the 2, right? 2 to the 2 is 4. So it means like you will have the contiguous 4 kilobyte pages. So it means 16 kilobyte. So all the pages here will be aligned with, you will get a lot of 16 kilobyte part. So the key idea is, at the very beginning, the physical memory, the physical DRAM will be partitioned into a lot of 2 to the maximum order area. So this area will then pick to move to the lower table. So from 9, actually it is 2 to the 9, right? So if maximum order is 10, then you can imagine like here are 1024 pages, and 9 will be 512, right? So the rest of the 512 will be moved to the next layer. So like add is like 2 to add is around like 256. So for this table, actually, it will maintain a 256 4 kilobyte area, and the rest of the 256 will be moved to the 7. So in this example, if a process requests a 2 to the 2 block, but there is no free pages in order 2 and 3. So actually, we will get it. For example, if there are something in the order 4, then the order 4 page will look like this. Like there is a one contiguous 2 to the 4 kilobyte. Okay, let's say it's 64 kilobyte. Okay, so we will first split it into half, like 2 to the 3, and then we will keep 1 2 to the 3 for the order 3 label, and the rest of the 2 to the 3 will be moved to the next label, like 2. So for 2, we will split it into half again, and then we will keep the 2 to the 2, and another 2 to the 2 will be returned to the request. So after returning this 2 to the 2, actually order 2, order 3, there are pages there. So the next time they can do a fast allocations. Okay, so this is about body system, and the next one will be the slab layer. So slab layer is the goal for slab layer is to group kernel objects into slab caches, and the kernel object should be the same. So it pre-allocate memory pages in slab, leading to faster memory allocation. Okay, so for example, there are a lot of data structure like this kind of text structure part, and then this is called a semaphore. So the semaphore management in Linux kernel, they are using these data structures. And then, for example, for inode is for the file. So for describing the file, you need this kind of stuff. But the thing is, actually, the text structure, the semaphore structure and inode structure, and also the memory management structure, those kind of structures, they are in different size. So if we mix those kind of things together and then store in the in the systems, there will be a lot of inner fragmentation. The reason is this size, and this size, they are not the same. So if we mix them together and then later on we just release, for example, the text structure. Okay, then in one pages, actually, if one text structure is released, then next, if there is other data structure is going to move into the patch, then the size probably will not fit. So they will cause the inner fragmentation. So a better solution is we will collect the same data structure together and store them together on the systems. So let me just directly jump to the key point. So like this, for this one, this is a contiguous memory. Let's say there are two pages here. So one page is 4 kilobytes. So for that area, we will only store one data structures. So in this example, we only store the text structure. Okay, so the reason to make this decision is because come to think about, if you remove one text structure, like one process is terminated, and later on, if one process is created, then that process can directly reuse this memory area without doing the patch allocation. Okay, so in this sense, we don't really need to always have the overhead for doing the memory allocation. We can reuse those kind of memory they are already allocated beforehand. Okay, so because we are going to reuse, so actually the slab there have maintained different kind of list. So for the full list, it means all the slabs under this full list, they're all used. So there's no space. And partial and empty, that means like they're partially used or actually they are all empty. So when the slab there occupies too much of the memory capacity, then the slab there management will release the slabs from the empty disk because they are all empty, so they can just directly return to the systems. So other data structure can use. Okay, but the thing is, the partial list actually we will keep because partial lists are those kind of slabs that can be used for other process if they have the same data structure needed to store in the systems. Okay, so this is about the step. Okay. So virtual address space. Actually, virtual address space is each process is given a unique and flat 32 or 64-bit address space. Oh, sorry. This process should be the user process because we say kernel process, they do not have a contact. They do not have a full virtual address space. Okay. Just give it, it's not important. So here comes an example. So usually your C code is look like this kind of stuff, right? You do include library to include a standard IO library, and then you usually will do, for example, to have some like global parameters like global -s, global -y, and then in the main function, probably you have your local parameters, your local variable, and then if you do the memory allocation for P, then maybe you will look at this. So this is a very typical C program. But how to put this C program map to the virtual address space? Like this. So the top tier is the kernel virtual address space. So no matter which process, they have the same things. Those are for kernel data structure, so it doesn't really matter for what kind of C code you're writing. The only matter parts will be here, the 3 GB virtual address space part. So for the text section means the whole C code. actually your C code will be stored in this section, code text section. So your code part is here. And there are two different kind of global variable. One is called initialize, the other is called uninitialized part. Okay, so the reason we are going to separate initialize and uninitialize is because for initialize, actually we can directly get from your source code, right? We don't really need to wait for the runtime. So it should be maintained in different way. And the reason, there are more details when we talk about VMA later. Okay, so we will have stack. So stack here, like we'll put our main function, our local variable, they're not given value on the initial part on the user stack part. Okay, and there's heap, like your memory allocation will get you'll put the data on the heap. Okay, so here comes the shared library part. So your send.io library will be get from this shared library. Okay, so this is the mapping. If you are going to map your like C code on the virtual address space, you will like this kind of stuff. So memory address is a particular value identified as the specific byte in the process address space. So if you are using a 32-bit address space, which means you have 2 to 32 byte. 2 to 32 byte is like 4 gigabyte. So if you have a 64-bit system, then your address space will be 2 to 64. So you will have a super large virtual address space. Okay, this is no matter how much of DRAM you are using. Like if you have like only maybe 16 gigabyte of DRAM in your 64-bit systems, it is also possible. Okay, so this part you can think about is separate. It doesn't really matter about how many physical DRAM you have. It only matters what kind of CPU you are using. You're using a 32-bit or you're using a 64-bit. Okay, so, but how to manage this kind of, orange area? Because each area is a little bit different. For example, their permission will be different. For text sections, actually it is about the executable because you have an executable code, right? But for some other kind of, for example, your stack and heap, actually, usually it doesn't really need an executable permission. So, so here comes the data structure called the memory descriptor. So memory descriptor is a kernel data structure, contains all information related to the process address space. So different data structure with the same content, all the memory area in the address space will be linked together. Okay, so last time we say actually there are two different data structures to maintain the same group of the virtual memory area. So one is using linked list, the other is for using the red black tree. So the reason is just because actually we will usually do different operation on the VMA. Sometimes if we are going to search a certain VMA, or sometimes we are going to traverse through the whole VMA. So Linux kernel maintain different data structures for the same data for different usage. Okay, just want to let you know that's the reason why we have different data structure here. So let's come to more details part. This is our memory structure. So for memory structure, for our memory descriptor, it is going to maintain the mapping between the VMA, okay, the relationship between the VMA. So the first field is about VM area structure. And this actually is one VMA. So actually, if we use a visualized part, it will be look like this. This is the memory structure, and there is a node called MM. This pointer will point to this VM area structure. So for this VM area structures, actually you will get the start and next. So each start and next is like this. We will map to one virtual address space. So you can think about this as a data structure for maintain a virtual memory area. So virtual memory area can be like the BSS, the code segment, or like your heap, your stack, your library. Okay, and inside there are a lot of pages because we say each virtual memory area that should be in a contiguous interval in a given virtual address space. So they are all contiguous on the virtual address space. So this is a VMA, and VMA is maintained is managed by the VM area structure. Okay. So the VM area structures will be maintained by the memory descriptor structure. So this is the hierarchy for how to manage the VMA. And actually, maybe you have a question about how to get this memory management structure, the MM structure. Actually, in the text structure part, there is a pointer called MM. The pointer inside the text structure, or the pointer in the process descriptor, can link to this MM structure. Okay. Okay. So let me give you some examples. Like this is the things we just talked about, like text section, data section, BSS section, heap, memory mapping, and user stack. And there is a term called anonymous. Actually, in Linux, you have a lot of chance to see this word anonymous. Anonymous means there is no file packet. For example, if you are talking about the data sections, the text sections, there does a file like your C code, your C program, right? You need to run your text section. Sorry, you need to run your C code, so the C code is put on the text section. And for the data section, it's about those initialized things. So because in your C code, there's a lot of initialized parameters, so you can directly get from your C code. Okay, but for BSS and heap, actually they are called anonymous because it doesn't depend on any like file on your systems, because heap and BSS, they are all allocated on the fly. They are all dynamic memory, and then these are all initialized parameters, so they were all given in the runtime. Okay, so here comes your process. There is a text structure to maintain your process descriptor, and inside the text structure, there is a field called MM. So with using a memory management pointer, you can get this MM structure. So with this MM structure, there's a field called mmap. So mmap will point to this. This is one VM area structure. Okay, so in this VM area structures, you will get a lot of fields here, right? So the start and end means the starting for the virtual address, and end means the end of the virtual address part. Okay, so actually the size is not the same for each of it. I mean, text section, data section, they are all in different size. So we need a start and end to let us know how large it is. Okay, and there's a thing called VM-file. Oh, sorry, I just cropped it, so there's not in this. But I mean, if you go to trace the Linux source code, there must be a thing called VM-file, and the VM-file will point to a file if this is a file packet. So for example, if this is the text section, because we need to know where is the source code. So the VM-file will point to the place you put your source code. So probably it's in the /binary/executable. So your code will be there. Okay. Okay. So the next one, you can get the next one by using this pointer called VM next. So VM next will change to another VM area structure. So another VM area structure usually is data sections. So data section is for the variable, the initialized variable. So the same things, we will get a start and end, and the permission actually here now is read and write, because we will not really execute on the variable. So if you come back to look at the text section, you will have read and execution. There is no write, because after you compile your source code, you will not really write your source code, right? You will not change your source code, and the thing is, but you will do the execution. So the permission here is VM-execution. Okay, so for the data sections, because those are for initialized parameters. So initialized parameters, they are all defined in your source code already. So this VM-file will once again point to the same place, your source code. Okay. And because we say BSS section are for all uninitialized variable, so actually there is no file packet. There is only read and write permission, and there is no VM-file. The VM-file will directly point to the null. Okay. Same as the heap. So for the heap, the same things. Actually, because heap doesn't have no file packet, so we don't have a like file here. Okay. So because heap usually it will grow during the runtime. I mean, depends on where you call your memory allocations and how large it is. So if sometimes you call a memory allocation with a super large size, then probably maybe you will split into a different virtual address. Then in this case, you call it many times, then you have a lot of virtual address. So you will chain together like how many times you call your function, and there will be how many VM area structure for this hit. Okay. So memory mapping for shared library. So shared library is another thing quite interesting because you can see shared library is like your standard IO library, other kind of library. So those kind of library, they're executable. And then if we are going to run the library, actually we need to know where is the object. So to get the object, actually it is usually under your Linux path like /library/ libc.static object. Okay. So here we can link our library to the shared library part. Okay. Okay, so it will maintain a VM area structure for each file. So for example, if you have you code different library, then this will be chained together, like you will need different VM area structure. And the rest of it is about the stack. So stack, actually, this is very similar to the heap. But the difference is your stack will grow down according to Linux. So there will be a label is called VM-grows down. So your stack will grow down and your heap will goes up. Okay. So this is about the like virtual address space part. So any two VMA cannot overlap with each other. I mean, we can call the find VMA to get the nearby VMA and check in the VMN field. So to make sure they are not overlap with each other. So if they overlap with each other, we will merge to VMA if they overlap with each other and if they have the same permission. Okay. So how to create or expand a VMA? So here is a thing called do-mm. So this function add an address interval to a process address space. So it means to expanding an existing memory area or creating a new one. Okay. So if you look at the, function, this do-mm function, there are several things you can control. The first is about like if this is a file packet, then you can give it the destination of your file. But if this is the anonymous, for example, if you're calling for heap, then you don't really need to give it a file. And here comes the address, the initial address for finding available space. Okay, so because you will first use the find VMA first to find where is the VMA, like then you can know where will be the available address, the starting point. So here is the thing you need to put, and then how large you are going to have, and then what is the permission, like if it is a read, write, or like executable, and then like the file offset if there is. Okay. Okay, so those are all about the virtual address space part. Then the next we are going to talk about is, okay, we have the virtual address space, like you know how your code is mapped on the virtual address space, but how to link the virtual address space with the physical address space? Because actually this structure here, it doesn't have any relationship with the physical address space, right? I mean, with this structure, it is good for structuring those kind of virtual memory. We can know, oh, this virtual memory is for heap. This memory is for the BSS. But how to link with the physical address? Okay, so before talking the detail about how to link with the physical address, let's give a very quick example. So actually, in our CPU, there are two very important hardware for doing the mapping between the physical and virtual address. One is called TLB, and the other is called MMU. So TLB is like a cache. So you can think about it's just like a cache for caching the patch table entry, or a more general thing is called the translation result, because we need to map from the virtual to physical. So we call one of it a translation. And the translation result you can directly store in TOB. So just like given a VA plum and what is the PA plum. So if we already know what is a PA plum, then we just store this pair in the TOB. So next time when CPU asks about, okay, I'm going to get a VA again, then your TOB will directly return you, oh, the PA is what? Okay. So if you already did the translation before, then you can check the TOB. Okay, but if not, I mean, if no matter if the TOB is too small or like if you don't really do this translation before, this is the first time, then inside CPU, your memory management unit will help to do the translation. Okay, so if not in TOB, then your MMU will run. Okay, one key thing, the reason we say the MMU will run is because there are also cores inside the CPU. So CPU cores can run other things. CPU cores do not really need to help on this process, because this process it needs to access the memory. So usually it takes a little longer time than CPU core to run other process. So actually, when we are doing the translation, CPU use the MMU to do a translation, then CPU cores can use to run other more important or like more critical things than page translation. Okay, so what MMU do is, what MMU does is like it will check the page table, and page table is also stored on the page frame. Okay, so all the data should be stored on the page frames, no matter you are page table or you are the data, those kind of stuff. So MMU will check the page table, and then after checking the page table, you will get the physical address. So after getting the physical address, the CPU can get the data according to the physical address. So probably if this is the data stored on PA, then CPU can directly get it. Okay, so we are going to talk about hash tables. Okay, so for systems with virtual memory management or MMU, all virtual address should be converted to physical address before being accessed. Okay, and most of your systems, no matter you're using PC or like your mobile, your server, for most kind of PC now, your CPU has the MMU. Okay, so there is only very like resource constraint, like tiny edge device, there is no MMU. So for those kind of device, there's no virtual address. So rest of them, I would say like more than 90% of your device, they have MMU. So it should do the virtual address to physical address translation before being accessed. So this step usually takes sometimes. Okay, and then it runs frequently. So it is quite important in terms of the system performance. Page tables take the responsibility for address translation. So each page table comprises a bunch of add by page table entries on 64-bit systems. Okay, so because this is a 64-bit, so you can think about like add byte is like 64 bits. Okay, so we will let you know why we need like this kind of 64 bits things, what each bit means. Okay, so the size of page table is proportional to the memory size. So usually larger memory, then you need more PTU. So the overall page table size will be larger. Okay. And Linux use the multi-level page table to do the access, because the reason to use a multi-level page tables is usually it is like faster, and then it can be architecture dependent. So there is some specialized room for do the optimization. So without optimization, CPU should access memory for looking up a page table each time. And TOB here comes. TOB is a hardware cache to keep the mapping between the virtual address and physical address in a CPU. Okay, so with TOB, actually we can like remove like a percentage of the translations. So it helps on performance. So CPU raise a patch fault when a process access a memory patch without proper preparations. So there are two different kind of improper preparation. The first is called a minor patch fault. So patch is already in the memory, but it's not marked in the CPU as being loaded in memory. So usually, like when you're using a memory allocation, the memory allocation will allocate the physical address once being touched, which means, for example, if you allocate like 4 GB area, so at the very beginning you can only get a 4 GB virtual address, but you'll not really get the 4 GB DRAM space at the very beginning, because in most cases programmers will allocate more DRAMs than they were really used. So Linux is going to adopt this kind of on-demand patching. So for this kind of on-demand way, actually, when you touch your virtual address, then your virtual address will do a link between the virtual and physical. Okay, so this is the reason there is a minor patch fault, because at the very beginning you have a lot of virtual address being allocated, but most of the virtual address they are not linked with any physical address. There comes another is called major patch fault. So major patch fault is patch is not in the memory. So for example, if you are going to get the data, your patch data, and probably if the data is swapped out, then there will be a major patch fault. Okay, so for a major patch fault, actually it will cause expensive I/O movement between the memory and storage. So when people are talking about the patch fault, people are talking more about the major patch fault because it takes a lot of time. So we say your CPU will do the context switch after handling the major patch fault. But when your CPU is handling a minor patch fault, actually CPU will not do the context switch in most cases, because minor patch fault is just about to link your virtual to the physical address. So usually there's no data movement there. Okay, so for handling minor patch fault, there is no need to do the context switch. Okay. So how the CPU works patch tables? Okay, so let's take 64-bit system as an example. So actually for the systems with 64 bits, it will be like this kind of stuff. Like here are 64-bit. So for 64-bit, actually you can address 2 to the 64 byte. So 2 to the 64 byte is super huge. There are more than petabytes, so it is quite a lot. So due to this reason, actually we don't have that much of need to have using all the bits. The reason is the more bits you are using, probably you need to translate more layers. So current Linux, you only use 48 bits here. So you can see this is 0 bits to 48 bits. And the rest of it, 64-bit to 48-bit, there are 16-bit that are unused. Okay, so the best address of PGD is maintained in CPU CR3 register. So here is the PGD offset. So you can think about this is the first patch table. Okay, so because for your CPU, if your CPU is going to kick off your MMU to do the translations, actually it needs to know where is the best address for the first patch table, so that it can start to move from the first layer, second layer, and then the third layer. So for CPU, it stores to the PGD offset, or for CPUs, it stores the best address for this PGD patch tables in the register called CR3. And this is only for Intel CPU. If you're using an ARM CPU or like other architecture CPU, actually like RISC-V CPU, actually they were stored in different defined register. So it depends on the architecture. Okay, because our register is the things depends on architecture. So Intel, they're using CR3, and the others, they are using different. Okay. So the key thing is CPU can work automatically by uploading to the MMU, and kernel code can also work it. Okay, but in most case, CPU will work it alone, and your kernel code will not really work. Your kernel will work when some kernel function needs to work the patch table. So it is quite different for the use case, because your CPU get a virtual address and CPU will do the translation to the physical address alone. You will not really ask the kernel help. Okay, the kernel is when there is a kernel programmer that need to trace the patch table, then kernel can also run it. Okay, So in this example, like it is about how CPU work it. So we say there is a bus address that are stored in the CR3, right? So CPU will check its own CR3 register, and CPU will know, oh, actually the PGD bus address is here. Okay. So this is the patch global directory table, or the first patch table called PGD. So inside the patch table, actually there are a lot of entries. So entries, each entry is 8 bits. Sorry, 8 bytes. So this 8 bytes look like this. This is called an entry. So there are a lot of different entries. So first of all, this PGD offset, if we are going to do the translation according to this one, so CPU will first split the 48 bits into 5 parts. The first part, second part, third, fourth, and fifth. So the first part of the PGD offset will be used to augment with the PGD bus address. Okay, because PGD bus address will point to here, right? So if you add the PGD offset with the PGD bus address, then you can know which entries like we are looking for. So bus address plus the PGD offset. So it means this is a bus address. So if you plus the PGD offset, like you will point to here, for example. Okay, so CPU will know, oh, actually PGD offset get and this PGD bus address means you are getting this PGD entry. Okay, so CPU will read out the PGD entries, and once again, this PGD entries will point to the bus address of some other patch table. For example, this is a second layer, so this is called a patch operator, the PUD table. So this is another patch table. So your PGD entries will point to here, another patch table. So you can think about this entry is pointing to another patch table, and this entry is pointing to another patch tables. So each of the patch entries, they will point to different patch table. So this is the reason why we said patch table can be super large, and it can support a super huge physical memory translations. Okay, so the same thing is, if this is the PGD entries, then what we are going to do is we are going to add the bus address of these PUD tables with this PUD offset. So this one is the target. We are going to do the translation, and here this part, they are all in the patch frames. They are all in the DRAM. They are all already there. So what we are going to do is just to find out what is the translation result of this 48 bits. Okay, so we always will get the offset from the target virtual address. Okay, so after finding the bus address of the second patch table, the PUD, we'll get where is the PUD offset. So using this 9-bit to concatenate with this PGD entry, the bus address part, we can know where it is. Okay, so the reason is why it is possible to only use this 9 bits and we can get this, this location of the entry. The reason is the 9 bits means like there are like 2 to the 9 possibility, right? 2 to the 9 possibility is 512. Okay, so for 512, like there are 512 entries inside each pages. Okay, so if we are going to get each of them, we just depends on like which bits it is, then we can know, oh, where is the entries. Okay, and then with the bus address and this 9 bits, we can decide, oh, which entries like you are going to point to. Okay. So the same things with your PUD entry, it is going to point to the next label, the third label's bus address. Like it will loop, because what we are going to do is find the bus address and then get the entry. So this bus address will point to the third label of the patch table. It is called a patch middle directory table. So this is also a patch. So a patch frame. So this patch frame, actually you get a patch frame and then you use the PMD offset. So again, PMD offset is a 9 bits stuff. So there are 512 here. So according to which bits combination it is, then you can get, oh, maybe this is here. Okay. And then after getting the PMD entry, the PMD entry will point to the best address of the last level patch table. It is called a patch table. Okay. So inside the patch table, once again, there are 9 bits again. So 9 bits here is 512. Okay. So here comes, if you do the 9 bits and then concatenate with the best address of the patch table, then you can get the final patch table entries. Okay. So actually, this patch table entries, if you open up, then this is this one is a 8 bytes, right? If you open up, there is a 64 bits here. So for this 64 bits, there are, we say the top 16 bits, they are reserved, they are unused. And then for the bottom 12 bits part, they are called control bits. So the only things that are important is the 12 bits to the 48 bits. There are 36 bits, they are called physical address. Okay. And then the very beginning of the 12 bits, actually, they will be directly replaced by the patch offset. So actually, this physical address plus the patch offset is the physical address of the patch. Okay. So in Linux, they will replace this control bits with the 12 bits, like patch offset. Then you can get the physical address. Okay. So this is one translation from the virtual address to the physical address. Okay. So maybe we can take a 10 and then we'll come back later to have a deep dive into why there are those kind of bits. Okay.哦，哎，然后你的电脑吗？还是
会有的点，但是这样子我也不记得。
哦，还是你给我 link？你有需要跑东西吗？
应该会跑一下。
哦，好，那
不过如果你没有的话，
其实也可以，我想一下哦，还是这样子，你进来，然后我等一下给你权限，然后你直接分享画面，然后你就一样，你就接这个，然后你就分享画面，然后对，这样应该可以，反正他的录影应该会继续录，对。
要把你现在这个声音，真的，
All right, so let's come back. So actually, we just go through the translation from virtual address to physical address one time, right? Before doing the second times, let me go into the details about some tricky part. Actually, this whole design, they are all CPU architecture specific. I mean, because this is an I should put it like this. This is an example for Intel CPU. So this all of it, they are based on the Intel CPU's design. So if you're using the RISC-V or like CPUs, then this in most cases will not be the same things. I mean, for example, your terminology parts, there is no PGD, PUD, PMD for RISC-V or those terminology there are for Intel. And also CR3 is not the same because for other CPU, they don't have CR3 register. And there are also some details here. So we say we reserve for 48 bits here, right? And then why we are going to split the PGD, PUD, PMD, and page table to the 9 bits, but why page offset is 12 bits? So actually, there are reasons behind the decision to make it 9 bits. And the reason is we say one page table should be put on one page frame, right? So one page frame is 4 kilobyte. Okay, and we say in this page frame, we only store page table entry. So you can see no matter this is the PGD entry, PUD entry, PMD entry, or PT entries. If you look closer, actually they are all entries. And entries, we say the size of entries is 8 bytes. So each of them, they are all 8 bytes, 8 bytes, 8 bytes, 8 bytes. So 8 bytes means 64 bits. So if you do some mathematics, you can know if you divide 4 kilobytes by 8 bytes, actually you will get 512, right? There are 512 8 bytes entries in the page table. So we are going to locate each entries. So we need 9 bits because 9 bits is 2 to the 9. 2 to the 9 is 512. So using the 9 bits, we can use the least amount of bits to decide which entries we are going to access. Okay. So the same things, because all of those page tables, they are all in a page frame size. So they are all for 9 bits because the entry is the same 8 bytes and the page table is the same. So this is all 9 bits. Okay. And the thing is why the less of page offset is 12 bits. Why not less also be in the 9 bits? So the reason is our page size is 4 kilobyte. So the last part is going to locate the data inside this 4 kilobyte size. We say our CPU is byte addressable, right? So byte addressable means the minimum granularity is a byte. So for 4 kilobyte, it means you are going to decide 4096 bytes there. So to decide the location for each byte, you need 12 bits because 2 to 12 is 4096. So this is the reason why the data table is 12 bits. Okay. So with this one, actually it is about where is the data inside a page. Okay. So come to our next step, like we just go through it, and the next step is we will read out this entry, and the entry is 64 bits. And the same thing is we will ignore the top 16 bits part. So what we only care about is the bottom 48 bits. For this bottom 48 bits, actually only this 12 to 48 bits, only this 32 bits is used to decide where is the page frame. Okay, so this part, the physical address part, is going to decide where is the location of the page frame. And the bottom 12 bits is, for this page frame, it is 4 kilobyte. So what is the data inside this 4 kilobyte? What bit location, what byte location it is. So we will use this 12 bits to decide the location inside the page frames. So put it together, 12 bits and like 30 to 36 bits, this 48 bits can decide the byte location for a certain page frame. Okay, so this is the reason why there are 9 bits and the last is 12 bits. Okay, so I think I did it a little bit fast, so maybe we can do this translation again because this is quite important. Okay. So, sorry. One more time. Okay. So we say we're going to use CPU to work the patch table. And then each time CPU will fetch the instruction, and the instruction should be in the virtual address. So your virtual address in a 64-bit system will be like this. This is a 64-bit or 8-byte. Okay. And actually, for the translation, we will first ignore the 16 bits because in kernel Linux, we only use a 48 bits. So the top 16 bits there is not used. And then your CPU will know actually there are 5 parts for the 48 bits. The top 9 bits is for navigated to the to the second page table. And the second part, the PUD offset, is going to navigate it to the third page table and the fourth page table and the final page table. And then you can use your patch offset to locate the byte address inside a patch frame. Okay. So at the very beginning, actually, this is only an offset. So offset means what is the data in the patch frame. But the key thing is where is the patch frame that we are going to look at, or where is the patch frame for the first patch table. So this cannot be translated by using this entry. So this is the reason CPU needs a register to store the base address for the first patch table. Okay, and actually, when you are doing the context switch, while we are saying like we are going to switch the patch table, the meaning is we are going to switch the content for the CR3 register. Okay, because each process has their own different base address. For example, this is process 1, so the base address is here. Maybe process 2, the base address is other. Okay, so when we are doing the context switch, if you go back to the slides, you can see there is a step as we need to switch the content inside the register for CR3. We need to switch to the patch table for that process. And when we are saying to switch the CR3 patch table is we are going to switch the top tier patch table. Okay. And the rest of it, actually, it doesn't really matter because the rest of it, we can get the patch table according to this translation step. So the only thing happens in context switch is we only switch the top table of the patch table. Okay. So after getting the base address from the CR3 register, actually the base address will point to the location for the first patch table. But when CPU open the patch frame, actually there are 512 entries there, right? Because each entry is 8 bytes. So if this is a 4 kilobyte, so we have 512 entries, and we are going to know which entries we are going to look for. So CPU will once again use the PGD offset. I mean, the MMU will concatenate the PGD offset with the base address. So this is what MMU does, this plus things. Okay, and actually this part, the kernel function has the same mapping part. I mean, if you open the kernel function, there's a thing called pgd-offset. So here is the function part. Okay, but this part can also be finished by purely using MMU. So this part can be run by purely hardware or purely software. So it just depends who codes these functions. Okay, so with using the PGD offset, we can get the PGD entry out. And actually, PGD entry is the same thing like this kind of stuff. Okay, so with using the PGD entries, we can know where is the base address of the next table. Because if you still remember, we said we only need 36 bits. We can know where is the next patch frame. Because the last 12 bits is we are going to know the byte inside the patch frame. So this is inside the patch frame, and here as we are going to decide the 36, 2 to the 36 patch frames. Okay, so with using the middle 36 bits part, actually we can get the base address of the second patch table. Okay, so for the second patch table here, actually you have another 512 entry solution options here. So we will use the PUD offset to guide about, so where is the third patch table, okay? So probably it's stored in this PUD entries, and then the CPU will read out the PUD entry, and this is also another add byte. So CPU will only use the middle 36 bits to to point to the best address for the third table called PMD table. Okay, so for this PMD table, we will do the same things. The CPU will use this PMD offset. It's another 9 bits to decide so where it is. Okay, so if we look to the last label, actually, here comes the last label. This is the 4 kilobyte area, and your PMD entry point to this patch. So you will use a 9 bits to get about where is the location for the patch frame like we are looking for. So actually, this patch table entries, the content inside this patch table entries means where is the physical address that we are looking for. Okay, so if we open up the patch table entries, you will look at this kind of stuff. And then the middle 36 bits means, oh, actually your patch frame is stored in these locations. Okay, so your CPU will once again concatenate, your MMU inside CPU will concatenate the 36 bits with the patch offset. So in this case, you can get the byte table information for that patch. Okay, so and then we are finished. Okay, so the thing is, if there is no TOB, that kind of stuff, then we need to do 1, 2, 3, 4. We need to do 4 memory address, 4 memory access to get the final result. So you can think about for each time, if we need to pay off 4 memory access to get the translation result, it takes a lot of time because CPU run any instruction in nanosecond level, right? I mean, the cycle, if you are using the 3 GHz CPUs, then probably your cycle will be 0.3 nanoseconds. But for each time you touch the DRAM, because those are all in the DRAM, because they are all patch frame. So in the DRAM, like for example, if this is like 32 nanoseconds access, then 4 of them we should be more than 100 of nanoseconds. So it takes a lot of time. So in current systems, actually, if you have a TOB and you can directly ignore all of the translations because you already know where is the physical address. So with the best address, you can directly, so with the virtual address, you can directly get the physical address out according to TOB. So TOB helps a lot because this translation should run every time when you get your virtual address. Okay. So this is about how CPU works the patch table. Okay. So question. Okay. So one extra thing to let you know, actually, why this design is quite tricky is we have talked about maybe 1 or 2 times, like there is a thing called huge patch, right? So huge patch means a larger patch. I mean, a larger virtual patch or physical head, the same. So we say now we are using regular patch is 4 kilobyte, right? And huge patch in Linux, so in Intel CPU is 2 megabyte and 1 gigabyte. It cannot be any other between them. You cannot get a huge patch as like 8 kilobyte, 16 kilobyte, or like 64 kilobyte. No, you can only get 2 megabyte and 1 gigabyte. So why we cannot get the different size of the like huge patch? So this is also because of translation. So if you look at the translation again, we say the last part is 12 bits because 12 bits can decide the byte information inside a 4 kilobyte area, right? Because 12 bit is 2 to 12 is 4 kilobyte. But the thing is, look at here. This is 21 bits. So 21 bit, if you do some calculation, 2 to the 21 byte is 2 megabyte. So this is the reason why for Intel CPU, the second larger page size is 2 megabyte. Because if you do the translation, you can do the first level, second level, and third level, and you can stop here. And then the rest of the 21 bits you can use to locate the data in the 2 megabyte area. So this is the reason for 2 megabyte. And the same things, as just mentioned, the largest one usually for the Intel CPU, the huge page can be 1 gigabyte. And the reason is, if you look at this level, it's 30 bits. So 30 bits means 2 to the 30. So that is 1 gigabyte, right? So with this 30 bits, actually, you can do only 2 translations, and then you can address the whole 1 gigabyte area. So this is the reason for 1 gigabyte. And there's one cool thing is why people are saying like using huge page can alleviate the translation overhead. It's because if you are going to get the 4 kilobyte area, then you need to do 1, 2, 3, 4. You need to do at most 4 memory access at most, because I mean in current CPU now they will have a lot of TOB, so probably you can catch each level as possible. So maybe you only need 3 level or even 4 level, but at most you need 4. Okay. But the thing is, if you use 2 megabyte page size, then you only need to do at most 3 access. So you can save 25% of the access in theory. So the thing is, if you use 1 gigabyte page size, which means you only need PGD offset, PUD offset, you only need 2 translations, then you are finished. The rest of it, 1 gigabyte, you don't really need to do. So you can save half of the translation code compared with the regular page, the 4 kilobyte page. So this is why huge page is, I mean, in some cases, huge page can help to improve the performance. Okay. Okay. So, actually, there are some tricky things for a control bits, but I have no space to draw it. But you can imagine, actually, for this 12 bits, there are some usage, because this 12 bits is not helpful for, it's not really help on the translation result, but because you would already use your target virtual address and you will use this 12 bits to replace this 12 bits, right? So in terms of getting the translation results, this control bits doesn't help. But in the process of translation, this 12 bits is super important. Because here comes a quick question is, how can CPU know if the physical address is in the CPU or not, in the memory or not in the memory? How does CPU know when to trigger the page flow? And how does CPU know what is the permission for this target page? So they are all in this 12 bits area. So each of bit means different different things. For example, 1 bit here is for present bit. Present bit is if this kind of data is in the storage or in the memory. Oh, sorry, if it is in the memory or not. I think I should put it like this. So present bit is if the present bit is set, it means hey, actually your data is in the memory. So if the present bit is not set, it means your data is not in the memory. Okay, and there is also another thing. It's called access bit in control bits area. I mean, probably somewhere, something here. So the access bit is, I'm not quite sure. Maybe it's also 1 bit. So this access bit is if this page is accessed or not. So when you are doing the LRU or like pseudo LRU, one very important thing is we need to judge whether this page is accessed or not. So this is the place why the CPU know, the control bits will tell the CPU, hey, actually this page is accessed or not. Okay, and also the permission. I mean, if this page is locked or if this page is like read-only, write-only, those kind of stuff, they are all in this control bits. So control bits is quite important because before the next step to get the data from the physical address, the CPU will first check the control bits to make sure this access is valid, this address is legal. And after checking if it is legal, then we will replace the control bits by this page offset, then CPU can get the physical address from the page, okay? So the next things before hand over to the TA is why 4-label page tables for 64-bit systems? I mean, why not using like 5 label, 6 label, or even 10 labels? What is the reason behind using the 4 label? So let's do some mathematics. So here, if we assume our page size is 4 kilobyte, we say it's 2 to the 12 bytes. So our virtual address space, we say we have 48-bit virtual address space. So we have 2 to the 48 bytes of the room for the virtual address space, right? And we define page table entry is 8 byte. Oh, actually, this configuration, they are all based on Intel. But the thing is, you can change it. I mean, you can say you want your page size to be 8 kilobyte, but you should not use the Intel CPU. You can customize your own CPU if you have. Then you can customize all these kind of things. I mean, you don't need to follow the page table entry size as 8 byte. You don't really need to follow the page size. So this calculation is for any CPU, not only for Intel. But in the calculation, I take Intel as an example. So 4 kilobyte, 48 bits, 8 bytes. Then how many labels there are? So the key things for this calculation is the first label, the top label, the global page table should be fitting 1 page frame. Okay, so coming back to our translation, the page table will, because we only use 1 register to point to the base address for the top label. So, which means your first label page table can only have 1 page, can only be fitting 1 page frame. Because the reason here is, if you have a second label page table, actually you can have at most 512 page table here, because each entry points to 1 page table. So your second label here, actually you have maximum 512 options for those kind of page table. Okay, but now you just pick 1. Okay, but for your first label, you don't have this kind of option. The reason is you base on the register, and the register can only store 1 base address. So your upper label of the page table should fit in the page frame. You can be smaller than the page frame. Let's say you can use fewer than 512, but you should not be larger than the page table, the page frame size. Okay, so this is the key things for doing this calculation. So let's first take a look, the last level. So for the last level is, we say we have the 48-bit virtual address, and then we need to first know how many pages we can do the addressing. So you will divide 2 to the 48 by 2 to the 12, because the page size is 4 kilobyte, and the page size is 12 bits, and this is 48 bits. So you do the calculation, actually there are 2 to the 36 pages at most for the last level. Okay, so 2 to 36 pages, we say for each page, you need an entry to know where is the location. So entry just look like the address you use to find your, just like your home address to find your home. You can think about 1 page is like a house. So you need 2 to the 36 PTEs, and total 1 PTE is 8 bytes. So the total size for this PTE is 2 to the 39 byte, right? 2 to the 36 times 2 to the 3 bytes. So your last label's PTE should be 2 to the 39 bytes. Okay, but obviously 2 to the 39 bytes is way more larger than 1 page size. We say 1 page size is 2 to the 12. So this cannot be the topper level. So you have the second level. Then the second level is you are going to find a PTE. So you need to fit those PTE into pages. So you will do the calculation, 2 to the 39 bytes divided by the page size, 2 to the 12. Then after these calculations, you know, oh, actually there are 2 to the 27 page tables needed for accommodating, for storing those PTEs in the first table. Okay, so the same things, because now you have those page tables, so you need the address. Each time you always need the address, because you always need the home address to find a house. So the same things, you also need a PTE. So 2 to the 27 page tables, actually you will need 2 to the 30 bytes. because the same thing is the PT is the add byte. So you will do the calculation and you will do the 2 to the 30 add. So 2 to the 30 bytes here. So once again, 2 to the 30 bytes cannot fit in a patch because the patch is 2 to the 12. So you will once again need another label. So you come to the third label. So the third label is 2 to the 30 page table entries. You are going to fit in how many pages. So you do the deviation, you divide by the 2 to the 12, then you can get, oh, actually there are 2 to the 18 page tables there. So 2 to the 18 page tables, you will get 2 to the 21 byte PTE size, okay? Which means here are 2 to the 18 PTE, and if you multiply with the add byte, then you can get a size. And once again, 2 to the 21 cannot be fit in the 4 kilobyte, right? Because this is slightly larger than this. So you will go for the fourth label. So the fourth label is you do the same things, okay? And you find like actually you only need 2 to the 9 page tables now. So 2 to the 9 page tables, if you times with the add byte entry, actually this entry is overall as 2 to the 12 bytes. So it just fit in one page. So you are finished. We are finished there because we need 4 labels and then we can store the final labels PTE in one page. Okay, so the thing, it is also possible if the last label is fewer than the size of the 4 kilobyte, it is also okay. You can stop here. But the last label cannot be larger than 4 kilobyte. Okay, so you answer actually you need at least 4 label page tables to finish this. I mean, you can have like 5 and 6 and 7. You can have a lot of page tables, but at this you need 4. Okay, if you use 3 label page tables, then you will need more than one CR2 register. You will need more register. So you will increase the register codes. So you need more area inside the CPU. Okay, so okay, that is the calculation about why currently under these configurations we minimum need 4 label page tables. Okay, so that's it. Questions for this part? All right, so if there's no questions, then I think we are around there. So let's hand over to your second hands-on.要登入吗？我走一下。你有你名字吗？有这个吗？
对。
好，然后我给你权限，然后你用你的电脑讲好了，我把我电脑静音。OK。嗯。好，可以。谢谢。好像不行这个，哎，可以吗？要试试吗？我发现它这个都要给电才可以。这个如果不行的话，就
那就用老师的。
对。好像可以。
可是这样我好像看不到。
然后这个可能一声，还是你这边可以开迷我啊，迷我回来。它可以了。哦。那不行，那我看一下。感觉这是需要的。
好，有这样子。
但你要分享画面。
好，
你可以把这个拉回来，
这个
对对对，你直接这样。好，可以。然后你把那个，把它拉到这边来 ，Webex，这样子比较好用。
这样，
对。要拉到这个上面那个，这个，对对。然后你这边共用一下。
哎，我现在已经有空了。
哎，为什么？哎，可是，哎，你先停一下公用。然后你再公用一次。哦，对对对对对对对对，哎，这个，然后等一下我要，好，可以了。
Oh, okay. So, this is the second assignment. It's about scheduling policy demonstration program for Linux. And this assignment is we want you to get familiar with the Linux scheduling policy. There's introduction. So the first one, Linux has four categories of four scheduling policy. The first one is a fair schedule policy, and there's a complete fair scheduler. It's what you have learned in your class. And the second one is real-time scheduling policy. It's about scheduled FIFO and scheduled RR. And the third one and fourth one is idle scheduling policy and deadline scheduling policy. Because you have learned about the complete fair scheduler in your class, so in this assignment, we will focus on this one, get normal, it's CAS, and the other one is real-time scheduling policy. And you will need to write a program to demonstrate how Linux will manage and interact with different kinds of scheduling policy. So we'll talk about what is schedule FIFO. So FIFO is a kind of a real-time scheduling algorithm, and it's without time slice. If it is with time slice, it is RR. So we are going to use the sketch FIFO as well without time slicing. And it's how it works. It's when a FIFO thread becomes runnable, it will always immediately preempt any currently running thread with their scheduling policy. So you can see the FIFO thread as it is the highest priority. After finish the FIFO thread, the Linux will then schedule other like complete fair scheduling, but it will have some kind of difference in the config in the system config setting. So we'll go through it. So for this assignment, you will need to reuse the environment in assignment 1. So the first thing you're going to do is like you need to get into the Docker container we provide to you in homework 1. And then you are going to create a new workspace for this assignment. And then you are going to reuse the kernel image and the root file system folder that you have built in your last assignment. So then you can go through it and start to implement the details. And it's about how to run the test program. Is then because we are going to run the program with the REST-like environment. So you need to cross-compile your program in the Docker container. And then you're going to copy the compiled REST-like program to the root file system we have provided to you. And then you are going to repack it just like the last assignment. And then you are going to boot with the commune with the REST-like environment. So next, I will talk about the implementation part. So in this assignment, you are going to implement a program And this program will then demonstrate how the different Linux process with different scheduling policies and how it will works on the Linux scheduler. So you are going to run, we have provided you a demo program called Sched demo, and there's a lot of arguments. So you need to find out what it stands for. So in the main thread, you are going to write a program that will pass the program arguments, and then you are going to create the worker threads, the number you have specified to you. And then you're going to set the CPU affinity. And then you're going to start all the threads at once, because if you start all the multi-thread in different time slices, and you'll get the output that is not what you want to simulate. So you are going to use some function, something like set affinity or set parent or set policy, and the other thing is the pthread barrier weight. So I strongly recommend you, if you are not familiar with pthread now, maybe you can try to learn what is pthread and how it works and how to program with pthread. So that's about main thread and the worker thread. Oops, sorry. For the worker thread, you are going to write a busy waiting thread to like simulate that the thread is working on something. So you cannot use sleep or nano sleep, some function like this. It will make the thread to like sleep and it will be blocked. So you are going to simulate the busy waiting. And finally, you are going to write a make file, and you are going to write make clean to make sure that your program can be compiled on a test environment. So if you are not familiar with makefile, you can refer to the links below. So that's all about the implementation part. So we have provided 3 public test cases for you. And we have provided you this file, this script, and this demo program on E3. So you can refer to them and download. And after you have compiled your program, you are going to run this command to make sure that you have passed all the 3 test cases. And the last thing is that you can use, you can change the text script we provide for you to make sure that the test case with the custom setting can also run successfully. So that's all. And the submission, we are going to make it 50-50. The 50% of this assignment is about the implementation part. So we are going to test your program with hidden test cases. And the other 50% of this assignment is about the reports. We are going to answer these questions. Okay, so I think I will quickly demo. Oops, sorry. Okay. So, Okay. So this is the Docker part. You can check the Docker container you have built in the homework one, and you are going to run with it. So if you follow the assignment stack of the homework one, you can find that you have already have a folder names with init.ls and Linux and the homework one. So in this assignment, you are going to create a working directory, which is named homework 2. And all of your implementation will be done inside this folder. So we have provided a demo program and a test script with to you, and the test script is this one. So after you finish your part, you are going to write a makefile, which will make sure that your test program can be compiled. Okay, so now you have finished your part, and you are going to repack all of the compiled program, like your implementation and the demo program provided to you, and the test script to the initial FS, and you are going to repack it with the command we provide to you. So I think is, oops. And after you pack your initial FS, you're going to run the programming to Mu Simulator. And you need to make sure that the argument is correct. And we are going to set the SMP argument with the 4 cores setting. And now you can run your test program. And the last thing you are going to do is make sure that this setting of the real-time throttling is correct. You can check with this command. So now you can see the setting is like it's not the correct number. So you are going to reset it. So after you have done this part, you can check the sorry. You can check this one. And make sure it looks like this. And the first 2 threads is like real-time process, and the last one is the complete fair scheduling policy. So I think that's all. So if you have any question about assignment 2, you can just reach out to TAs. We'll reply you in the email. Thanks.
So, any questions for this part? So, if there's no, then let's call it a day. So, about for your reason. So for the guys online, let's call it a day.
Perfect. So we have the time. We have sample questions for the midterm, so we can review them.
Yeah, even a sample question.
Yes.
I think you can directly check the internet. There are some samples already there.
So
Yeah.
before you uploaded some sample questionnaires.
Not really, just like there are some true and false questions, and then there are some like description about like personal keyword description about, for example, what is the schedule or those kind of stuff here. Prior, I mean, exam last year in the internet, you can go check here. Yeah, yeah, I think you can find it on the net.
Yeah, I'll try to find it.
Yeah, yeah.
想问一下，就是为什么中文可能有点基础，就为什么12个bit 它等于4KB 啊？
因为这个 bit 其实是说它有2的12次方这种可能性，然后但是
它说一个 KG 是2的9方，然后它是
没错，这个问题就在于说，这个是对应关系其实是一个 bit 会对应到一个 byte，因为我们的机体是用 byte 来做平均的，所以它这个是它可以去 address 到空间有多大。所以，因为我们说我们机器都是 byte addressable 的原因，就是因为这里虽然它是写一个 bit，但这有点像是它的地址。就是它的地址可能就是假设有12 bit 的话，它有4096个可能的地址，但每一个 bit 它可以对应到一个 byte，应该说它每个 bit 会需要对应到一个 byte，所以你是2的12次方是要乘以 byte 的，不是乘以 bit。
只在 CPU 这样吗？
就是 CPU 在管理机体是以 byte 来做管理。对，
在我们整个课程当中，一个 byte 都是在说一个。
就是
我们
整个课程中都是以 byte 的角度来看到，只是因为这里的话，它是定值是一个 bit 对应到一个 byte，所以基本上我们会说这个定值是从12 bit 对应到一个4096 byte 的空间。对。
好，就是
这要有点就是 tricky 一点点，对。
因为我本来公式也是现查的，我就是也不是很熟练。就是有时候还有一个问题就是。这边是不是就是说整一个 address 是由这5个 part 组成的，然后它就是一部分就是相当于一个那个 cascade 的模式组成了最后的我们整一个 address。
我觉得可以这样说是没错，就是它的
要一点点组。
你说为什么不直接组嘛？
对啊，一个一个就是。
因为
那就是把它组成。
第一个是因为这样 CPU 比较好设计，因为它这个设计是基于 CPU 去48 bit 去切的。那你说为什么不直接就是一次到位转过去？可是一次到位转过去有一个很大的问题是，你这个转换啊，它可能要就是很长的 table 它帮做转换。
转换
就是 virtual to physical。然后如果你这边是一次都只用9 bits 来做转换嘛，所以代表你一次只能去查到512个 page， 对吧？因为一个 bit 代表一个 page， 那2的9次方代表512个 page。但是如果你要把它用就是一层来转的话，那代表你这个 table 会很长，因为你的 page 可能很多，就你的 page 可能有几百万个 page。很多所以你的 page table 就变得很长。那你要查的话，你就要从第1个、第2个、第3个、第4个去查。对。但你如果把它切很多层的话，第一个点是它比较有机会可以放到主机体里面去，因为其实它这个 table 啊，就是你最后这边全部加起来的总 table 数目其实可以很多，因为它下一个地方其实就有算说，假设理论上来讲，我们有这个48 bit 的定值空间的话，代表你这边可以去定值到2的48。不好意思，2的48除以，因为它 page 才是4KB， 所以它是2的36个 page。2的36个 page 是就是几百亿吧个 page。
我以为这边是说 PTE 的 size 很大，我们
对 PTE size 也很大，
给它不断缩小，直到它能小到能放入。
哦，没有，这边的意思是说，我们这边。理论上可以有这么多配，当然它实际上不会有这么多啊，就是看你分配的时候分配多少。但理论上你可以有这么多2、36次方的 page， 所以理论上你也需要有2、36次方的 PTE， 因为一个 PTE 就是对应到一个 page。 那你这个236的 PT 总共加起来的 size 会是
乘以4，
再乘以800，8 bit。
为什么是8呢？哦，
因为它这边是 entry 的800，对，乘以8。
单位是 byte，
对，
然后但它其实也是1个 bit，不，
它800是64个 bits， 对。
这里为什么 byte 又等于8个？
这个没有 byte always 都等于是8个 bits， 只是在定值来说的话，你这边用 CP 用1个 bit 是可以定值到1个 byte 的记忆体空间的。
我们考试会考这个吗？
不会，但是这边还是会，就是你这个8个 bytes 就是等于8 bits， 那你8乘8就是64 bits， 对，所以这也就是为什么我们这边画的是就是0到就是不好意思，应该是0到63，没写错，就是总共有64个 bits， 就是这个总共是一个64 bits 的区域，对，那这个就是一个 entry， 然后你这边才会算说所以你这边第一层的话，你可能需要有
整个是一个 entry，
对吧？就是整个64 bits， 也就是整个8 byte 是一个 entry。也就是说你的地址有这么长，但你每次都只会拿一部分来去做，
然后这16个是没有用的，
是没有用的，对。
所以我们实际上是有36个 bit 的地方是放这个地址的，然后这上面是忽略的，
对，
然后这下面是
就是具体你拿到这个 page 之后，还有那个4KB， 可是你要4KB 的哪个位置？因为你这个36被转出来的是他会给你一个 page， 可是一个 page 有4KB， 但你在做存资料的时候，就是 ACID 资料的时候，你是需要知道你要存的哪一个 byte， 因为我们说我们记忆体是 byte addressable， 所以 CPU 可以以 byte 的形式去做存取，就有点像是你这边找到你家了，可你家里面有很多房间，你怎么知道你房间是哪一个？那这边就是在告诉你，那你房间可能是哪一间这样子。那这个12 bits 呢，其实就是2的12次方，就是可以定值到2的12次方的 byte， 所以它这边是可以定值到4KB 的，就是任何 byte 你都可以定值到，你就可以知道说是哪一个位置要被存取。
就是说，我们通过到这一步，我们得到了一个4KB 的 page frame，然后我们这一个就是具体定位到这个4KB 的 page frame 中的每一个 byte。
没错。没错。
好的，谢谢老师。
好
，OK，然后你先问我还有个上题。
好。
就是老师，请问一下，这整个架构就是我想问，这个架构是 text struct 会有个 mm 指向mm struct，
对，
然后 mm struct 在
有个 map 的 pointer 知道这一串，
那这一串是这里边的小东西吗？
没有，一个就是一个，
就是
它这边就是一个，这边是一个 VMA， 所以它这边这个 VM area structure 就是代表这个 VMA 空间。那这边那个橘色、深色橘色对应到这边深色橘色，浅色橘色对应到这边的浅色橘色。所以这边代表的是 VMA， 这边代表的是 VM area structure。然后它会用 next 去把它全部串在一起。这样。
所以我现在有点搞混 text structure 和 mm structure。它 text structure 真的有一个栏位指向 mm，
应该是在。你应该回去看第1章的时候，应该会有，它应该会，因为这边是被解掉，它下面应该还有一个是可以真的知道 mm 的地方。
所以一个 task 有
一个 process 就是一个 task， 对。
一个 process 一个 task， 然后它有就是一个自己的 virtual address space。
没错，所以每个 process 都有每个自己的 virtual address space。
然后这边方便只储存了可能必要的资讯而已，那它实际上还会再 map 到另外一个真正的记忆体空间。
没有，这边讲的是资料结构部分。就是这边都是资料，橘色都是资料结构。所以这资料结构是为了要去判断你这个区域啊有哪些权限。那你真正的资料 map 的地方其实是浅橘色这部分，浅橘色才是这个 virtual address space 的地方。对，那这个深橘色其实是资料结构来让 Linux 知道说哦，你这个 VMA 有什么特性，然后它多大这一些的。所以你真的资料其实放在浅橘色部分，深橘色其实是就是资料结构而已。
那所以我们先查深橘色，再查浅橘色。
没错。
哦。
所以我们深橘色是那个 kernel data structure 吗？
对，没错，它就是 kernel data structure。
嗯，
对，就是因为浅橘色是一个抽象的概念，就是虽然你知道这是叫 text section， 这个叫 data section， 好，那你也知道还有这个这么大的区域，可是你从程式角度来讲的话，你要怎么去管理这些区域？你怎么知道它的位置在什么地方，然后它的权限是什么？所以这个深橘色就是那个实作出来的 data structure 要去 describe 这个区域。对，好，
所以有点像就是那个深色的是宣告它的结构，然后浅色的它是它实际执行的。
没错，就是实际上放置在什么地方。
好，老师，我就是又找到一个，就是我刚刚问漏的，就是我们讲 TLB 是可以直接就是 pass by 这5个。
因为 TLB 对，因为 TLB 是个硬体的块区，所以你可以想象成，反正你最后你就是想要转出。
正好昨天查，他说它可以储存最近用到的
对
fetch table， 然后
转换结果。
所以它就是直接略过这5个，就是
它就是对，没错。
加的这个步骤，然后直接能得到什么呢？
直接能得到那个 page，就是
这
是36 bit 是多少？
就我们直接
对，就是你今天给一个
page frame，
对，直接告诉你 page frame 在哪里，然后你再透过你这个 offset，你就可以知道说你要拿到这个 page frame 的是什么地方。对，
所以我们可以看到三个部分，就是第一个部分没用，第二个部分得到 page frame， 第三个部分得到精确的这个 page frame 中哪个精确的位置。
没错。
那只是点到这边的这位置。
就是我们这块不是讲那个CPU 的 model switch 和 process 和 context switch 吗？
对。
我们上面那个process context 的定义就是说就是它对保存了这3个不同的环境嘛 ，user address space、hardware register 和 kernel data。那就是我们就列一个表嘛，对比它 process context，那就是我们把这个表看到这边，这个 CPU mode switch 我们是这样子的嘛，就是它只有这个PC 这里是，
对，
它就会用到这个，然后这2个是不会动到的。
它可能 PC 代表你之前把
就是对，没错，它只会把少部分的 hardware register 去做转换，因为 kernel 是一样的，然后 user address space 是不会用到的，所以基本上2个不会换。
kernel 一样的，就是一样。
对，然后因为 user address space 不会用到，所以它也不需要换。其实这个 mode switch 基本上做的事情就是把 CPU 的某一个 register 从0转到1或1转到0，就是从user mode 转到 kernel mode 的这个代表，然后把部分的 register 替换掉，因为你要知道你 kernel function 的那个 program counter 是什么地方，所以就是替换那少部分。那其他的跟 user 相关的 address space 或者是这个 kernel data structure 它就是不用动。对。
所以这个转 CPU mode 的代价非常小，所以我们在执行同一个 process 中，可以在同一个 process 内进行就是 CPU mode 的转换。
这也是为什么 Linux 要把 kernel address space 跟 user address space 把它合在一起。因为它可以透过 mode switch 的转换，就直接轻量的转到 kernel 去。那如果 kernel 今天是一个 user process， 或者 kernel 是一个完整的 process 的话，它就不能这样做，它就要做 process level context switch， 所以它整个 user address space 啊，全部都要转过去才行。因为现在的 kernel 设计不是一个独立的 process， 所以它才会享有这一些优势。因为你看user address space 代表每个 process 都一定要有东西，所以如果今天的 Linux kernel 是一个 process 的话，那它就是需要有一个独立的 address space， 那它就不能只靠这个 mode switch 你就去做转换。
不是说它一直都是这样做的吗？这是它新的创新点吗？
这是 Linux 这样做，但是微软就不是这样做。微软就是一个 kernel 就是一个 process。对，所以这个算是为什么 CPU mode switch 为什么 kernel 要这样设计，就是因为它的 CPU mode switch 比较lightweight。
特点。
对。
就是老师，我还有个问题就是，哎，这个是讲 system call 是个 bridge 嘛，就是连接 user process 和 hardware resource。
没错。
所以我们在实际的执行流程中，是不是就是我们 user process，然后先去跟OS 进行连接，然后 OS 去找 CPU，然后 CPU 去从 hardware 里边获取它要的就是 memory 啊之类的，然后进行执行。
我觉得概念可以这样理解，但实际上其实不是这样，因为实际上 OS 跟 user process 其实都是 CPU 在跑的，所以
老师你再说一遍。
OS 跟 user process 其实都是跑在 CPU 上的，因为它们都是软体。CPU 是个硬体，所以刚刚那样的讲法应该是在一颗 CPU 核心上面的某一个 user process， 它发出了讯号，那它发出的这个 system call 会中断现在这颗 CPU call， 那因为它中断之后 CPU 的下一个动作期就是会去，它有个机制就会进 kernel， 所以 CPU 就会现在改跑 kernel 的 process， kernel 的事情这样子，跑 kernel 对。所以其实大家都在 CPU 上做，只是谁现在就 CPU 现在在跑哪一个 task 而已。对，
所以这3个都是在同一个物理的地方。
对，没错，他们都是跑在 CPU 上面。
就是还有一个问题就有点，我们就类比到我们做的那个作业，就是比如说我们就是讲 user，就是它有一个要查表的，然后那个表里边我们定义了新的 function，然后我们把一个具体的数字和这个 function 连接在一起。
对。
那这个数字是谁在用呢？是不是 user 就是说我呼叫这个，比如说451，user 说我要呼叫451，然后那个表就是找到这个具体的 function。
没错。
所以 user 不知道我实际上呼叫的那个 function 叫什么，他只知道451号吗？
没有 ，user 应该知道，因为就是user，这个有点复杂，因为其实 kernel就是这个system code 是写 kernel 的人定义的。那写 kernel 的人跟 user 的人其实是通常是2个全不同的人。然后 user 的人也不会直接去 call kernel， 因为他还会有 library， 就是你的那些是拿 library。
2次转换吗？
也可以说至少2次转换，就是
因为我在写作业过程中我就发现了，我虽然一直在定义它是451号，可是我不管是 test 里边还是我的写的那个方式里面，是没有谁直接用到了451。
因为没错，因为你的那个 C library 帮你就是 mask 掉这个地方，就你如果从 user space 来看的话，你会跟 C library 来沟通，然后 C library 呢才会跟就是它下面还有很多层，然后最后才是碰到 kernel。所以其实你在写 code 的时候是基本上不会知道你那个 system code 是。
那我一直定义它450，就是因为这个451是我新加进去，我新，那我一直定义它的
用意是什么？因为你如果是你是正在 program kernel， 就是你在写 kernel function 的话，那 kernel space 就是要你去定义那个号码，这样你上面的那个 user library 才会知道要怎么去 call。
但这个号码也是我新加的。
对，但是因为你现在是在写 kernel 的人，所以你不是 user。我这边说的 user 是一般的 C 加加 C 的 program 那种，是 user。那你如果在写 kernel， 就是个 kernel programmer。
那我们简单理解就是说，这个号码是给 user 用的，可以这样理解。
这个号码是给 kernel 用的 ，user 不知道这个号码。
这个 kernel 用的。那我为什么 test C 就是我的 test 相当于是 user 端嘛？就我们测试这个 function，相当于那个 test 文档是吧？那 test 里边也 define 了这个号码。No。
有吗？
有啊。
你们在 test 里面是 define 那个号码，那我去哪了吗？
不是，他就是
对啊
define 了，他就是写了这个 define，但是也同时也呼叫了这个 function 的名字。
因为就是实际上你的 library 看的其实是
名字吗？
就是你那个名字是什么？然后我记得 library 它是会有一个对应，就是说知道说library 给一般的 user 看到的是名字，但是 library 自己有一个表格是存名字跟数字，然后它是把这个数字给 kernel， 所以 kernel 其实认数字。
kernel 认数字，那我写的方式 kernel 也只认名字，它名字要对齐了才能跑成功。
那是那个 function name 吧？那是 function name 吧？对吧？
我也不是很确定，所以我才会有这个疑问。
就是
发现我一直在努力堆砌所有的名字，跟数字一点关系都没有。
数字应该只有在一开始你在做宣告的时候要定义说你要用哪一个数字作为这个function。对，因为它有点像是它其实就是 interrupt 变形，因为你 interrupt 你要给定一个数字，让可能我知道这个数字有没有人用，如果没有人用的话呢，你要让它做什么功能。但那个功能就是你在你的 kernel function 里面定义的那个名字，那个功能那个名字跟那个数字这样能够对起来。对。然后至于接下来你要用名字抠还是用数字抠，我记得是都可以，就是你可以是给你的 ID 是多少，还是你要直接用那个 name。对，所以它是需要一对一对应，通常是需要一对一对应的。对，
好，谢谢老师。
好，谢谢。
哎呦，哦，只是我们最后，这个机制，我可以想象成，就是我们原本有那么大的一个 page table，然后我们为了节省记忆体用量，不要耗那么多，所以我们把它拆成很小的，先把它分成很多部分，然后越切割越细。所以有可能有个例子是 PGD entry 指到的是 none，就是没有，因为没有储存空间。
那
就是我的意思说，就我可能只用到那么小的记忆体区块，那实际上这边就
你说这个边没有填满的状况，
对啊，
对，有可能。
然后讲义上这例子是有填满的状况，就是刚好我们可以连到最后的 PTN 去。
对。
然后，
但是说实在，就是你应该是说你这边可能会没有，所以你上面本来你这边会有512个 page table，但你最后可能实际上你只会有就是10个或者是3个这样子。对，因为你没有用到，你就不需要把它分配出来。对。
那实际上记忆体是 physical address 存在 PT entry 吗？还是会把这些东西 concat 起来？
什么意思？
就是我们最后要得到 physical address，从 virtual address 得到。
没有啊，就是你这边读出来就是 physical address 啊。
这个
它是每一步这样下来，所以你跟前一步基本上就不会关系了。就是它是走4步，第4步的时候你这边拿出来的就是最后的 physical address 的结果。
所以这个36 bit，这是每一个 entry。
对。
那么大，然后这个只有9 bit。
没有，这个9 bit 它会指到是那个一个 base address。
所以是 base address 加，
因为这个
bit 会变大。
这个打开来是一个
就是36 bit， 8 byte。
这个9 bit 是指这边总共有512个，它一个 PGD entry 都是8 byte 的。所以每个人里面都是就是64 bit 的一个位置。那你这边拿出来的位置是直接指到某一个 table 的底而已。
它是直接指到，然后
就是它会直接指到这个 page frame 的一开始。对，然后这个 page frame 里面因为是放 entry，所以它有512个可能性，所以它用这个 offset 去定位说，所以是哪一个 entry 这样子。
指的不是 page table 吗？
指的不是，对啊，但是 page table 它是存在 page frame 上面。
不是说 page table 是
page table 是一个
概念，
就是它是一个，对，你要讲它的概念也好，反正它就是一个类似资料结构，但是它实际上它是要存在就是敌人上面。
不是说 page table 是 virtual memory 的，然后 page frame 是 physical memory 的吗？
没有 ，page table 是一种资料，但这个资料就存在某个地方。
也是。
对，但它存的地方其实就是敌人上面。对。
然后敌人是 physical。
敌人是 physical。对，所以这每一张 page table 你可以想象它都是放在一个 page frame 里面。对。
实际上 page frame 就是这么大。
对啊，就是每个都是一个 page frame，一个 page frame。
他是查完了，就走过了这一步，他就忘了上一步，然后他就再走下一步，就是他最后不会说，他不会存下来这一步吗？
就是没有用。
其实如果我在现在系统来讲，它是会存下来的。因为现在的系统它是有很多 TOB，所以你可以存这个，存这个，所以它不一定是走4步，它很有可能就是走2步，然后第3步就已经有结果了，所以它就会直接给你结果。对。
就这个介绍法呀。
对，但是 我觉得有点复杂，所以我觉得你可以先理解成没有 TOB 的状况。对，因为它每一步都可能会有 TOB，所以它每一步可能都转一转之后呢，它就会有结果直接给你讲。对。
哦，如果有 TLB 的话，会把中间储存起来，到时候直接找就好了。
没错。
那我们这个就是 maintain in CR3 register 就全部都在这个 CR3。
没有 CR3 register 就只有一个，它只有一个8byte 的对应而已，就是只有这个，这是一个8byte。
哦，就是我们 base
对
的 address。
它只会存，因为它是 register 啊，所以它只会存一个8byte。
然后这个 base address 跟我们后面的其实没有关系。
有关系，你要知道。
除了这条线有。
就是这条线，就是你要知道第一张 table 在什么地方。
base 是对所有的 virtual address 对吧？
没有，这个 base address 是对这个 PGD 的 base address，就是你可以想
PGD 的，还是就只对这一个 virtual address 的 PGD？
应该这样讲，它是对这个 process 的 PGD。
那所以说不同 process
会有不同的 PGD，
会有不同的 base address。那这个但是不同 process 它就会换。
没错。
哦。
对 context switch 就换这个，就是你每个 process 它就换一个 CR3进来。对。所以每个 process 的 page table 是不一样的，就在这个地方。
对啊。这个也是8bit 吗？
这个是64bit 8byte。
每个
就是8byte。对，
每个 process 都有自己的 PGD
每个 process 都有自己的对。
那所以一个 process 都需要这么大的空间。那真的假的？
但是你不会，但是重点是你不会用满啊。就是你理论上这个是可以定制到这边2的36次方个 page， 所以你这个在线上这 page size 的话是超大的，但你一般不会用那么多，所以 page table 也是按里面建，就是你用多少用多少，一般就用什么4GB 而已，那你才用到就是什么12次方而已。对，所以一般 page table 理论上不会到那么大，但是你说你要是真的你的 DRAM 超大，你有什么Zeta byte 的 DRAM，那有可能你的 page table 就会需要这么大。对，所以我觉得这个是一个比较弹性的设计。对。
这一个很大吗？
很大，就是你这边理论上你用完，你光最下面这层就需要有2的39次方个 byte 来去存这个转换的结果。2的39次方个 byte 相当于是多少啊？2的9次方的 GB，512 GB， 对吧？对吧？你就光这个转换你就要512 GB 了。对，但你一般不会用那么多啦，一般就是几 GB 就已经很多了。对。
那这边是8byte，那因为是在64bit 架构上，如果是在32bit 就是4byte，是吗？OK，
没错。就是几 bit 就是看你是用几 bit 的 system， 它就可以定制到几 bit 去。对。好，感谢。好，感谢线上的各位，那今天就到这儿。